In this video, we're going to be taking a look at the maximum product problem, which is very similar to the maximum sum of a subarray, right? But it's a little bit different in the way that we structure and build it out. So let's talk a little bit about the problem first. When we were adding together numbers, it made a lot of sense for us to just keep adding until we reach something that ends up smaller, and then starting again from that point and seeing if we could grow to be something bigger after that, right? With multiplication, it becomes a little bit more tricky. You'll see with the situation of positives and 0, it's pretty easy to apply that same technique. We keep multiplying the numbers together until we reach something that makes it smaller, and then we can continue on from that point, right? And that applies basically the same sort of process as the addition-based problem we saw previously. However, there's a catch with multiplication, and that's negative numbers, right? You can multiply a negative and make a positive. So in this sort of situation, it doesn't make sense for us to necessarily restart each time we get smaller. If you consider this example here, we have 2, and then we have negative 10. If I were applying that principle, I would start back at negative 5 and then start multiplying again. If I were to do this, I would actually miss the actual optimal product. The actual optimum product here would be 2 times negative 5 times negative 5. That would make 25 times 2, which would be 50, right? Because there's 2 negatives, it ends up giving us a positive value. So we can't apply the exact same process, but we can do something pretty clever with it. And that clever thing is, on each iteration, we're going to keep track of the largest product we've seen, but also the smallest product we've seen. Because it turns out that if we keep track of the smallest product and we end up multiplying by a negative, it could flip to a positive and become the biggest product, right? So we're going to keep track of both of those pieces of information, and that allows us to account for this negative and positive idea. It's basically keeping the 2 different sides of the multiplication active, right? So let's talk about the actual code for this. It looks very similar to our sum code with some small differences. We're going to keep track of the current max and the current min, which I'll initialize both to 1. Then I'll take my result, which will start at nums at 0. And I'm going to say for n in nums, and iterate through that whole set there. The values that we could possibly have, that we could choose, right, would be n, which would be just to take the number without doing any sort of multiplication. I could take n and multiply it by the current max, or I could take n and multiply it by the current min. And to determine which one is best, what we do is we just update the current max and the current min to be equal to the max of vals and the min of vals. So basically what's happening here is we get the maximum of these 3 values equal either n times the maximum, or n times the minimum. We also get the minimum of that, right? So the smallest possible outcome and the largest possible outcome. Then all we have to do from here is just say the result is equal to the largest of either the current res or the current max. And that's all that really needs to be done. From here, we could just return res, and we're done. So you can see generally how this process is going to work for us, right? We're just going to generally compare each of these different values to each other and determine which ones are going to give us the proper maximum. And as I'm looking through this code, I'm sort of realizing, okay, so we take the max of the res and the current max, but actually we should also take the max of the res and the current min, right? Just in case the minimum, well, in this case, the minimum is going to be the smallest of those values. So actually, in this case, this would be kind of redundant to do, right? Because generally, we're going to get that max already out of here, which is going to in turn compare these 3 values. So the min will always be the small. So actually, this is as good as we're gonna have for this. So this will be okay. So this gives us the full-on solution. So again, just to reiterate, basically we keep track of the maximum and the minimum each time. We see if multiplying by n ends up with a bigger maximum or a smaller minimum, and we keep track of the maximum each time, and we return that result back. Just to show you that this does actually end up working, we'll run this with some of our examples. So let's take a look at this one right here, the 2, negative 5, negative 5, negative 5. This one is going to give us a value, I believe, of 50 as a maximum sum. Let's take a look and see if that is correct. You see that we do indeed get 50, right? And we can see that if something has just like straight up incremental values, right, generally we'll also get a solution as well. In this case, 120, which would be these 3 multiplied together, right? So that's just another example of a way that we could do this maximal kind of optimization. Just another note here is, again, the differences between like the different operations that we have. When we look at problems like these, we're really trying to approach them from their unique properties, right? We know how to find the maximal subarray. So if we have a problem that looks very similar to that, we want to take a look at what properties are the same, what properties are different, and see if we can change our working solution into one that is going to fit this new set of parameters or bounds. So in this case, we see that we are able to do that very cleanly in this sort of example here. So thanks so much for watching this video, and I'll see you in the next one.